everyone. So we're actually going to talk about precipitation variability and statistics in this instructional video. So the outline is we're going to focus on precipitation observations, moments of data, graphical representations of precipitation data, as well as precipitation for engineering design. So on the bottom left, if you want to follow along, I have where we are in the presentation. So first, starting with precipitation gauges, we have non-recording gauges. So this is basically like somebody is volunteering a piece of their property and they have a standing gauge that measures in precipitation accumulation over time. So it is manually observed. There's a 24-hour collection period. And so there's a 9-inch non-recording SRG gauge, which is shown here. It's composed of an overflow can, measuring stick, collector tube, and a funnel. Usually it comes with a measuring stick that's used to measure the depth of the water with a resolution of 0.01 inches up to 2 inches. The second type of gauge is a recording gauge. And so I'm going to talk about a couple of different varieties. The first and probably most common is called a tipping bucket. It automatically tips and counts for every 0.01 inch. And it basically calculates total precipitation it calculates total precipitation by the total number of time it tips. The second type of gauge is called a weighing gauge, and this collects all types of precipitation continuously into a bucket. So the primary difference between these two gauges is the first gauge, the tipping bucket, will only tick, it will only count as long as we hit some threshold, right? So every 0.01 inches, it will count. This weighing gauge will count continuously. So it's actually quite useful to have this type of gauge if you're interested in recording precipitation in a specific increment. So for example, you can record every 15 minutes, every hour. It just depends on what you're looking for, and that will determine the type of gauge that you use. Now, we have a ton of gauges distributed throughout the United States. This is kind of a snapshot into Southern California, provided by NOAA, the National Climate Data Center. And so every single dot is an observation, a precipitation gauge. Now, you would have to click on each dot to determine the time frame, the reliability of the data, what's available. It might be precipitation as well as temperature, wind speed, like other parameters could also be available at those gauges. And so you can see how really sprawled out these gauges are. It's not like you have an observation every 100 square feet, right? It's very scattered. So what we would typically do is we would get an estimate of our precipitation using statistical analysis. So the statistical analysis finds probabilities or moments of data. And so the examples I'm going to show you are kind of just random observations. So let's say we collected precipitation observations at this site over a series of time. And so that would be X, so a set of observations. And what we might be interested in is the average or expected precipitation observation over a given period of time. So you would sum your observations and divide by the total number of observations. Another way to calculate the mean in MATLAB would be mean of X, or in Excel would be average of X. So that's the first moment of our data. The second moment of our data is called variance. And variance is basically telling us how similar or dissimilar our data set is. So if the variance value is very high, high variance, that means that you have kind of a wide distribution of observations. If your variability is very small, a very, very small number, then that means that your values are clustered towards a similar value. So like clustered towards the mean. You would calculate the variance by taking the sum of the difference between each value, so each value of X minus the mean. So you'd sum the difference squared and then divide by the number of observations by 1. You could also calculate variance using engineering tools like MATLAB and Excel, using var of x in MATLAB or vara x in Excel. Another really common parameter is called standard deviation. And so variance is this Greek symbol sigma, and variance is sigma squared, and standard deviation is just sigma, so the square root of your variance. Again, it's telling us similar information. It's just a measurement of how variable your data set is. And in MATLAB, you can calculate the standard deviation using stdx, or you can calculate the square root of variance, which is essentially showing this here. In Excel, similarly, you can calculate standard deviation using stdev of x or square root of vara x. So you can use your tools to calculate the first and second moment of the data set. We do have a third moment of data set, and that's called skew. And that's just a measurement of the symmetry of the distribution. So again, if you're skewing left or skewing right, given some mean value, I provide the equation here for you to calculate. In MATLAB, there is a parameter called skewness, but skewness actually does not calculate skew. So that's why I provided the equation here. And in Excel, you can calculate this G, or third moment skew, using skew of X. So this is how you would calculate our statistics, our moments of our data set. Again, calculating these things are really important because it tells us a lot about the data set. So here we're showing how we would represent precipitation graphically. So we would generate something called the rainfall hyetograph. It's a plot of rainfall intensity or depth as a function of time, and it's often drawn as a bar graph. So if you like using MATLAB, you would just use this function bar, and then you enter your X parameter and then your Y parameter. You could also do this in Excel, where you would use the graph icon and then use something like this to generate a bar graph. Rainfall intensity is the depth of rainfall per unit time. Really common measurements or units of rainfall intensity are inches per hour or millimeters per hour. Another thing that we typically measure is something called cumulative rainfall hyetograph, or rainfall mass curve. And what this is a plot of accumulated rainfall as a function of time, and it's often drawn as a curve. So in this example, what we're going to do is kind of walk you through how to estimate the rainfall in the interval, given this column here, the accumulated rainfall in this period of time. And then we're going to calculate that rainfall intensity. So first, let's go ahead and calculate our rainfall in the interval. And so we're going to look at our observations here. So we have an observation every 0.25 hours. And so the first observation is just going to be 0. This is our initiation. We've experienced no precipitation. And then we measure the accumulation from the first time step to the second time step, which is going to just be the difference in rainfall here. So 0.02 minus 0, which is 0.02 inches. Okay. We do the same thing with the subsequent time step. So we're checking the difference between the third precipitation from the third time step minus the second, and this gives us 0.06 inches. We do this again, 0.2 minus 0.08, 0.12 inches, and then 0.24 minus 0.2, which is 0.04. And so what this third column is telling us is how much rain did we experience in each time step. The next column is rainfall intensity. So this is basically how much rain we experienced in a time frame of an hour. Okay, so this is a 0 here. And then what we're going to do is we're going to take our rainfall interval and we're going to divide it by time. And so that's going to be 0.02 divided by 0.25. So I'm going to calculate this with you. and that's going to be 0.08 inches per hour. We're going to get 0.06 again. And now look at this. We're not going to divide by the total time that we've experienced so far. No, we're only dividing by the time frame in which this precipitation event was experienced. So it's actually going to be the difference between these two time frames, which is 0.25 hours. So 0.25, so 0.6 divided by 0.25, and that gives us 0.24. Same thing with the next time step, 0.12 divided by the difference in the time frame, again, 0.25, and that's going to give us 0.48, and we do this again, 0.4 divided by difference in time frame, 0.25, and that is going to get us 0.16. So from this table, we can identify that this time frame here is when we experience the highest rainfall intensity, which was almost a half an inch in an hour. That's considered the rainfall intensity. Now what we're going to do is we're going to generate the graphs for each of these observations. So the first graph is the Hyetograph, and again, on the y-axis we have rainfall intensity, and on the x-axis we have time. So this is what a Hyetograph would look like, again, generating using a bar graph. This is our cumulative mass curve, where we're plotting our accumulated rainfall over our observation period. And again, if you're given, for instance, the rainfall in the interval, what you would be doing is you would get P1 is equal to P1. P2 is going to be P1 plus whatever precipitation you've experienced in the previous time steps. So this, actually, let me call this cumulative, and then cumulative. And that would be like that. And then CP3 is P1 plus P2 plus P3. So you can see it just keeps going down. It accumulates forward in time. So that's what you're plotting here in this graph, is just, you're just adding the precipitation observation and allowing the graph to grow, okay? Very helpful in showing and determining like how much rain did we experience overall, right? Let's say over the year. What it also can, I mean, if you have a longer period of observation, it'll tell you what seasons give you the most rainfall. It could tell you about just the general trends of the watershed that you're evaluating. So the time frames of interest. So a lot of the times we're looking at mean monthly, mean seasonal, or mean annual precipitation. I just want to bring it to your attention that we're actually we're talking about the totals precipitation for that time frame. What you're not going to do, okay, is you're not going to grab all of your January observations. Like, let's say you have 10 years of observations. So let's say this is year 1, year 2, year 3, and so on and so forth to year 10. And then you have a January, a February, a March, an April, a May, and so forth to December. Okay. What you're going to do is you're going to grab all of your January dates. Okay. All right. In year 1, year 2, year 3, and so on and so forth to year 10, okay? You're not going to just grab those precipitation events and you're not going to just average them. You're actually going to sum and get the total for that January, the total for this January, sum the total for this January, sum total for that January, and then you're going to take the average of the total Januaries. Okay, and that's going to give you your mean monthly precipitation. So if you were to go to, and that's part of the assignment for homework, is you're going to go to NOAA NCDC site and you're going to get the climatology. So the mean monthly precipitation, the mean of a specific gauge. That's what they're telling you. It's not that it experiences 0.02 inches on average over the month. No, it's saying that it's experiencing 2 inches in total on average for that month. Okay. It's completely different calculation. You would do the same thing if you're considering seasonal, right? So you would, and I have the months here on the bottom for fall, winter, spring, and summer. So you would take all of the dates that coincide with spring, for instance, that'd be March, April, May for this year, sum them, and so on and so forth. And then you would take the average of the sum to get your mean seasonal. Okay. And again, do the same thing for your annual. You would take the sum over the year, sum over the year, sum of the year, sum of the year, then take the average of that total annual precipitation. Like for instance, when we're in Los Angeles and we say we experience approximately 15 inches of rain on average, like that's our annual precipitation. That's again the total over the year. That's the total average precipitation. Okay, just wanted to make sure we understood that. Also, hydrologists typically use what's called water years. And so we would organize our time sequence into this kind of time frame that I show here, where we're actually showing data from October, November, December, January, February, March, all the way to September. I know it seems a little strange, but I'm going to show you on the next slide kind of why we do that. So this is a graph of the total monthly precipitation for a site. And as you can see here, it's organized again from October to September. And the reason why we do this is because we generate what's typically like a bell-shaped curve. It actually helps us see how our precipitation is distributed. It's just a better way of visualizing the year because all of the precipitation is in the center of the graph. So everybody does this. These are a couple of examples. The top graph is the statewide average precipitation by water year for California. So you can see here, very small print, but it says water year, October 1st to September 30th. It's just the way we generate our data set. And on the bottom here is a Los Angeles precipitation. Again, this data set is organized by water year. Another thing to note is that how we enumerate the water year. So October is actually the October of the previous year. So right now we're in 2020. We're heading towards the end of 2020. So we would, for this water year, we would use October 2019, right? Then we start our 2020, and this is going to be 2020. And this would be considered water year 2020, where the bulk majority of the precipitation is actually going to be from this point on, and that's predominantly in year 2020. So just so you know, you're not manipulating the year 2020 to move the months around. No, you don't do that. What you do is you take the previous October, combine it with the current September, and that's your water year. It's just the way hydrologists do it. Again, for your homework, that's something you're going to have to use. So now we're transitioning into precipitation for engineering design. And so there's something called a return period or a recurrence interval. And what this is an annual maximum event has a return period of T years if the magnitude of this event is equal or exceeded on average once every T years. So T is your return period. And the way we design our systems is we are designed to make sure that they can withstand what's called 100-year flood. And the reason why we do that is to protect homes, the people, businesses, like everything. We're trying to make sure our infrastructure is able to withstand this 100-year storm. So I'm actually going to share a story with you for this article. So this flood, this 100-year flood occurred in 2013. I was a postdoc at the Colorado School of Mines during this time frame, and what I remember was that my friend lived on the other side of this river that ran through towns called Clear Creek, and she couldn't get to her apartment because she had to cross a bridge. This bridge was completely flooded, and it was very dangerous, and it was deep. The water was incredibly deep, and she couldn't cross over to the bridge. So just to kind of give how extreme this was, this flood resulted in 20-foot walls of water rushing down the sides of the mountains. It affected 17 Colorado counties. It devastated most of Boulder and Larimer counties. I was actually in Golden, which is talked about a little bit here. The statistics were that they had 6 fatalities, 708 people unaccounted for, 11,700 people evacuated, and just kind of skipping to structures, 17,494 structures damaged, and about 1,500 destroyed. Another story, I had another friend doing his postdoc in CU Boulder, and his entire bottom floor of his apartment was completely flooded. It was 3 feet deep of water. Lucky for him, he was on the second floor, but he was trapped in that second floor for 3 days. So he didn't have access to electricity. He had no extra food. Whatever he had in there is what he had to survive on. So kind of jumping down into this 100-year storm, it says this storm has been referred to as the 100-year storm, but what does it mean? A 100-year flood or storm is an event that has a 1% chance of occurring in any given year. So it's so extreme, okay? There's only a 1% chance that it could occur. It says data from the gauge on Boulder Creek shows the flash flood had about a 1% chance of happening or a 100-year flood. So kind of how do we calculate this? I'm gonna get to that, but I wanted to share some more statistics at the bottom here, where it's talking about how much rain was received. So it says here are some rain totals for 1 week. Keep in mind, average yearly rainfall is around 9 inches, and so again, average yearly total. So it's 9 inches per year. It says Aurora, Colorado received 15 inches of rain in 1 week. Okay, so if we were to calculate the intensity, so 9 inches divided by 365, that's 0.024 intensity. Okay, intensity of 0.024. In this case, and for Aurora, Colorado, it's at 15 inches in 7 days. That's 2.14 inches per day. Okay, so they super exceeded the total amount of rain that they receive in a year in 7 days. It's pretty crazy. That is a 100-year storm. So again, a 100-year flood or storm is an event that has a 1% chance of occurring in any given year. So what we would do to calculate this is we would set T equal to 100 years, and then P, which is the probability of occurrence every year, is just equal to 1 over T. So P is equal to 1 over 100, which is 0.01, or 1% chance of occurrence every year. You can repeat this calculation for any other year. So again, a flood that we get every 2 years, a flood that we get every 50 years, and that would be, you can calculate your probability of occurrence. And this equation can be used for rainfall, runoff, stream flow, really anything.